To the next speaker here. It's Fred Rennig. He's from ST Microelectronics. I give you a short introduction of Fred here. After studying electrical engineering at the Technical University in Munich, Fred was working for AT&T and Lucent and Texas Instruments in Germany and the United States before he joined ST in 2004, working as project manager and design lead for automotive mixed signal ICs. Since 2010, Fred is working as a technical marketing principal engineer and member of technical staff as system engineer for automotive networking and network security. Fred, the floor is yours. Please go on with your presentation.
Thank you very much for the introduction. Let me share my presentation. So welcome everybody to this talk about a lightweight communication bus. This bus is currently under standardization and specification as CAN-FD Lite within this Canon automation as a CR standard. So before talking about the communication bus, let's have a look about the car network evolution and what brought us to the idea of developing a so-called lightweight CAN-FD bus. You can see here in the point to the laser pointer. So you can see here a well-known picture. I think most of us know it as the evolution of the car network. From a flat network that we had in the past, nowadays we are more into the domain-oriented network, where we have a gateway and domain controllers controlling domains like the connectivity, like the drivetrain, like infotainment and body and comfort and so on. And in the future, we'll also more and more move into a zonal-oriented network where we have some sort of a central brain and zonal gateways. And I would like to draw your attention to this cloud of devices that is quite often overseen. So let's have a closer look at that. First of all, what does it mean when we look at the zonal gateways? When we zoom into this network, we see that functions are now combined within zones. For example, the functions that are in the front left of the car, as shown in this example. And these zone controllers and zonal gateways here are connected to central processors. And so these zonal gateways and controller implement many applications that can run in parallel because we're getting more and more powerful microcontrollers and microprocessors. And we can separate and isolate applications running by using hardware hypervisors. So that means we can run independently different applications in the same microprocessor running on different cores and also maybe sometimes even on the same core in parallel, and they are perfectly isolated. And we see still these actuators and sensors that are placed at the end of the networks. So when we look here, they are connected to the zonal gateways, and they're usually controlled by these zone controllers. In today's networks, these are controlled by domain controllers, but zone controllers do basically, when we look into that, at least from the point of these sensors and actuators, basically do the same thing. In general, for these actuators and sensors, there's no software needed because they can run here within the zonal gateway. And we see that the move to this kind of applications and to this kind of architectures has already started. So what are the evolution drivers of this car network architecture evolution? Of course, we see more and more computation power. So the computation power evolves, and an increasing computation power leads to consolidation. Of course, we can, as I mentioned previously, we can combine more and more applications within the same hardware. And the applications can be separated by the mentioned hardware hypervisor. These zone controllers are now connected with high bandwidth networks. I mean, we are talking usually about gigabit networks, multi-gigabit networks, 10 gigabit networks in the car that manage all the traffic between the zone controllers and the central brain. So this is driving this network evolution. And of course, this leads to the architecture evolution that I've just shown. So this is the increased computation power, and the high bandwidth interconnects can shape the car architecture towards either a domain or towards a zone architecture, where we have the zone controllers in various locations within the car. But the question I would still like to ask is, when we talk about all these multi-gigabit networks and all these computation powers, where are now the sensors and actuators? And this is one thing where we looked at. Therefore, we said, okay, let's look as an example and look into the rear car as an example of what is going to happen in the future, even today. I mean, we see that already on the roads. So how does it look in the rear in the rear section of the car? When we look at modern car lights, modern rear lights, we see that there are many animations going on. I mean, we know these animated turn indicators, we see the coming home and light animation and so on. And for these quite appealing lights, we need many individual light sources. And when I talk about many individual light sources, I talk about several hundred, 600 and above individual light sources that need to be dynamically animated. So for that, we need many drivers here in the rear light. And for communicating with these drivers that drive these rear light LEDs, we need usually a microcontroller and the software for this high dynamics and safety very close to these drivers. So when I look here in the rear light, I need to move the drivers to the rear light. And then also we need some sort of a microcontroller very close to. But when we think about that, I mean, in the end, we have a distributed list of drivers, and the number of drivers for this rear light, we talk about 20 drivers and higher, and even more. They need to have anyway a very reliable interconnection to this MCU. So when we think of it, and we could think about it, would be good if we had a highly reliable network that can communicate with these drivers. And when we think about that, then not only with this MCU very close to, but directly with zonal gateways. So maybe in the end, we can get rid of this microcontroller in the rear light. So the question of this light-wide communication bus would be, it would be good if you had a network for this kind of application that is providing a good and a very high performance, but at the same time, it must be very cost efficient, because you need to drive around about 20 plus drivers for that needs to be connected to this network. So we cannot afford to spend a lot of money in each of those drivers. So no software stack, nothing like that. We will later on talk about very accurate clocks and so on. It has to have a high bandwidth utilization because of all these animations and the many drivers and the many LEDs light sources that we want to drive. And of course, when we think about the rear lights, we do not want to have it turn off. We don't want to have the turn indicators pointing in the wrong direction. So we need a high automotive grade safety for that as well. And therefore we came up and on the CAN-FD and invented this kind of the CAN-FD light bus at that time. So now look again at the next generation light design. Today we have this body control domain, which is here. As I mentioned, we have the rear light module, usually connected, let's say by a CAN bus, for example, could sometimes even be a lower data rate, depends on the power of this microcontroller. But usually you have a CAN bus here that is connecting the body control domain to the rear light module. And then you have some sort of bus, like let's say an I2C or whatever it was, to communicate with the rear light. But now the vision and the idea is to move to an architecture like that, to drive the drivers directly by a reliable bus directly from the body control domain, where we have these powerful ECUs and we have an application running that was previously running here and can now move into the body control domain. So we have no software anymore. We can do all the software updates over the air in the body control domain as we are used to it. So we are very flexible here in the body control domain, where we have to be flexible today anyway. And then no software in this area. So then we thought about what kind of communication concept would that be to use here. The first idea that we came up, yes, it has to be a bus network. Bus networks are very flexible. So we have the domain controller here. So the picture here shows our evaluation board. This acts with a microcontroller. So this acts as a domain controller. And these are the LED drivers, the light drivers for the rear light here. And then you can see we have here a bus network. So no daisy chain, no point-to-point, nothing like that. It's a bus network because a bus network offers several advantages. First of all, for a car architect, it is very flexible. I mean, you can change the topology depending where your domain controller is, what kind of lighting you have, how many lights you want to drive, so where the drivers are, and so on. So you don't have to think about routing this wire through these, like in a daisy chain, through these drivers. So bus network is a very flexible network to use. And then the bus network has another advantage. So whenever there's a message sent from the domain controller to the bus, this message, or this frame, as we used to talk in CAN, these frames are received by all of these drivers. So you can be highly efficient when communicating and sending frames to these drivers, which is very important if you want to have an animated light in the rear light when you want to drive several hundred LEDs. So the idea of the communication concept was first to use a bus network. Then we have a domain controller here, a light controller, whatever kind of application that runs. And so we have a light control unit, body control unit, and this can act as a communication commander. Because anyway, it controls all of these devices. So we can identify this here as a communication commander. And then we have these light actuators, the drivers for these LEDs, and they just respond. And so these are small monolithic devices. Everything, or almost everything, is integrated within these devices. So we have small monolithic devices that control the light sources, and they react only on a request from the commander. So these are communication responders. So we can introduce a commander responder communication structure here. And then we said, okay, what would fit best for this kind of application? And with a KNFD-based communication, we have almost everything we needed. KNFD offers a lot of benefits. It offers a very high bandwidth. So if we talk about KNFD and a standard KNFD, we can use 1 megabit per second bandwidth if we do not do bitrate switching. And then depending on how you update these individual dynamic light sources, we came up with numbers of up to 4,000 individual dynamic lights that we can address with the 1 megabit per second bandwidth. Of course, 50 millisecond update rate. If it's shorter than that, of course, the number of individual dynamic lights will decrease, and 8 bit per pixel, because usually the brightness is not programmed in a linear way for these real lights. So if the light is more dim, then you need a higher resolution, and if it's brighter, then you need a smaller resolution. So it's not really linear. So therefore 8-bit per pixel works in many applications. And then KNFD offers a low overhead, so the 64-byte data payload. And the good thing is it already offers a guaranteed edge density that we can use for synchronization, which is the famous bit stuffing rule. It's cost efficient. It's a bus network, so we can address several devices with one frame, and we can address through frame identifier. And it already offers safety mechanisms like the cyclic redundancy check. We have heard a lot about the cyclic redundancy check on the CAN-XL. Here for KNFD, it is proven. So it's in use already. It's in the cars, so it's very reliable and very well known. And on top of that, there's a lot of existing experience on the user side. In our case, mostly on the car manufacturer side. So first of all, we have a hardware protocol controllers and microcontrollers. So KNFD protocol controllers are there, and they are implemented already in hardware in the domain controller. So we do not implement anything in software here. The protocol is already managed. And most important at the car maker side is that the tooling environment is already available. So you can use your existing tools to analyze the network. So in case there's any issue in the manufacturing sites or at repair stations or whatever, you have the tooling already available to run your diagnosis. So a lot of benefits from the CanFD side. However, so there is so much light, sometimes there is also a little bit shadow. So there are a few downsides here. And one of the downside is that CanFD works with arbitration and also some error handling, like sending error frames and overload frames. And these two require an accurate clock. That's why in the CAN and CanFD networks, usually crystal oscillators are used, sometimes also ceramic resonators, and they're expensive. So for the arbitration, we have to account for sender phase shifts, and therefore we get this very costly ceramic resonator. And when we think about it, we cannot place at a maturity of drivers for actuators crystals. I mean, automotive crystals are really very expensive. So we cannot place them. I mean, even 5 crystals in such a real network would increase the cost significantly. And then the individual bus access is based on priorities. So we're not usually talking about the CAN ID as an ID, but it's also defining the bus access priority here. This is very nicely shown in the new descriptions for CanXL, for example. So that means there's not really a guaranteed time slot for the data transfer. We need buffer memory, which is in these small devices also quite expensive. And anyway, an answer on a data request may get delayed, and you cannot maybe really rely on a certain command sequence to drive your animations for these LED drivers. And then there are additional standardization features that need to be implemented and that we do not need. For example, the error handling with the error frames and error counters that are not required in such a commander responder scheme as I indicated previously. So therefore, we came up with the idea with a network which is CanFD compatible, and it's a communication subset. So the CanFD compatible communication is a subset of the already existing communication protocol. In the Canyon automation standard that we are developing, we say it's an implementation based on a subset of the CanFD protocol, to be more precise. We use a CanFD compliant transceiver. There's no need to reinvent the wheel here. We have very well proven transceivers already, and even for higher data rates and for complicated network, you just heard a presentation about the signal improvement circuit transceivers, about the SIG transceiver. So they are on the market and they are very reliable. They are ISO standard compliant, and they're also automotive certified with the so-called very famous Zwickau tests. So we have this transceiver and we can make use of them. The data rate I mentioned has enough bandwidth for more than 4,000 lights, and the hardware controllers exist. So how does it look like now, this communication protocol? So as mentioned, it's a commander-responder communication. So the commander ECU, which is our domain or zone controller, controls the entire communication. We can synchronize these responders to the data stream of the commander. So whenever the commander sends out a frame, we get the data, and then we can synchronize our internal timing of our communication timing to this frames that we receive from the commander. We do not arbitrate, so we don't need arbitration because of this commander-responder communication, and we do not need error frames because the communication sequence and the communication direction is clearly identifiable. So there's no need to advertise errors over the entire network. And in the end, what does it mean is we do not need a frequency setting external component. The frequency accuracy can be significantly less than that what is required in a standard CAN-FD network. Here we are talking about accuracy in the range of 3%, plus minus 3%, compared to plus minus 0.2, 0.3% for the standard CAN-FD networks. And then in the end, it means, and we can synchronize here to the commander, and in the end, this means the entire oscillator can be integrated in the monolithic device. So we do not need crystal oscillators or ceramic resonators. Frame requests and answers can be clearly identified, so this adds a lot to the communication safety. Excuse me. The responders answer only to dedicated commander requests, and the communication interrupts can then be clearly identified because I know which the commander knows from which responder to expect an answer. And if we have a dedicated communication scheme without arbitration, then also the responder knows within what time frame it expects a certain communication from the commander. So we can implement a watchdog. And with all of that, we also get a high bandwidth utilization. So we'll now have a look at the CAN-FD. The CAN-FD frame offers a lot, and we have a very limited overhead. We have this arbitration field that we can use for the standard ID, that we can use for addressing. We have several control bits. These are 6 overhead control bits that are fixed. Okay, we have to live with these 6 bits, but this is a very small price to pay. Then we have a data length code, so we are not fixed to a specific length of this data frame. I mean, we encode it here, how much data we want to send as a payload. It's up to 64 bytes, so it's very efficient compared to these control bits here. And by the way, we need them. I mean, we need some sort of an address field in the end, and we need the data length code. So therefore, it's a low overhead. We have the stuff bit count for additional safety to ensure the data integrity. And we have the cycle redundancy check field with this 17 or 21 bit that is very well proven and already implemented in hardware and the microcontroller. And then in the end, we have an acknowledge field that honestly a commander responder scheme does not really need, but it's there. It's simply part of the CAN-FD protocol. So the commander knows if there is any communication breakdown when he does not get an acknowledge. So this comes for free with it. And then of course the end of frame field. And then we also looked at the bandwidth utilization and at the actuator addressing. Therefore, we used 2 kinds of frames. We used broadcast and multicast frames and also diagnosis frames, which we called unicast frames. The idea of the broadcast frames is to make use of the bus topology. Therefore, we can send on the bus broadcast frames to all of the responders that are on the network. For example, like setting a PWM number for the brightness of the LEDs. So with 64-byte payloads, you can theoretically program within one frame the PWM with 8-bit of 64 drivers for 64 LEDs scattered over several devices. Because you can send it to all devices at once, so we can make use of that. That's why we implemented broadcast frames, and exactly because of the bus architecture. And this allows a high update rate for the dynamic light pattern. Of course, with this kind of broadcast frame, you do not expect a response from the drivers, but you don't need it in all cases. And then for diagnosis, to get back diagnosis data from individual drivers, there are these so-called diagnose or unicast frames. So the diagnosis requested a lower update rate. It's not needed to be as high data rate as the broadcast frames to set the brightness of the driver. But then within a certain amount of time, you want to request if there is any diagnosis problem. For example, you want to check if there is a short at the output driver, if there's an over temperature and stuff like that. And you do not need to do that with every frame. And with that, each device can be requested individually for diagnosis data. So the responders answer only to unicast frames addressed to them specifically. So again, we have this commander-responder communication. Responders answer to dedicated commander requests only. They do not initiate a communication. There is no responder-responder communication allowed. So therefore, the responders can always synchronize to the frame coming from the commander, because they do not expect communication between different responders. And the accuracy, the clock accuracy, the data rate accuracy is very high coming from the commanders. Erroneous frames are just in general simply ignored. They are dropped. So there's no advertisement of errors along the network. And that means also you can implement timers, watchdogs on both communication ends, because the commander can check how long does it take until it gets an answer from a dedicated responder. And if the responder does not answer, then there's a communication problem. And on the other side, the responder knows within what time frame it has to receive a communication request from the commander. And then you can implement a watchdog there as well. So you can implement this as a communication safety, and then the drivers can enter some sort of a fail-safe state, like turning on the rear lights, for example, if there is no bus communication. The error stop the responder side, error stop the frame reception. So the responder enters in the sort of bus integration state and simply waits for the next frame on the bus. So whenever it detects an error, then it just said, okay, I discard what I receive. Then I wait for a certain time as a bus idle time. And then the next bit that I receive, the next dominant bit, is then a start of frame bit. So then I will get the next frame, and then I will start decoding the frame again, receiving this frame again. They do not send any error overload frames, so because they are not needed. And this can be also used for some expansions if somebody wants to implement it. For example, like using the IDE bit, or like using the bitrate switch bit in case of need, and in case some expansions can be implemented. So that means it is also open for other kind of implementations. And the responders do not need the acknowledge bit. They simply ignore it, or they say, okay, in the end, once I have received the correct CRC, I have received the frame correctly, and I'm done. So when we look at that, we see a dynamic light pattern. So this is a video of our prototype, of our test boards. So we send the broadcast frames. They have some properties. We assigned devices to a chain of devices, and also we tell the devices where to find the data within the broadcast frame within the 64 bytes payload. And this is initialized at the beginning. So every device gets assigned a chain number, and then also position where to find its data, and then with the responder ID at the chain initialization sequence. And then the broadcast frames can be sent, and then each of these responder can pick the data from this from this 64 bytes or 512 bits, however you may want to look at that. Unicast frames work simply the same. Whether it's a broadcast frame or unicast frame is then encoded in the ID. And there's also the responder ID. We said we use the first 2 bits to indicate that. And on top of that, we implemented a protocol which we derived from our own ST-SPI protocol in the unicast frame. So in the end, what you do, the commander sends an opcode which says read write to a specific address. It sends the address, the memory address, and then the data bytes belonging to the address, and the responder answers with a global status byte indicating if there's any error occurred, like as I mentioned, temperature shutdown or any kind of a short condition at the drivers, and then responds with the memory location. So with that, you can program memory locations individually with these kind of unicast frames, and you can also get back data, get back the diagnosis data, and also you can monitor the content of these drivers, like is the PWM correctly received, are the lights on, and stuff like that. This is a full monolithic implementation. So we have here implemented KNFD transceiver. It's on the device. It's fully certified. Of course, it has to, otherwise we cannot use it in the network. Then there's a KNFD light communication protocol controller with device memory. And then there are some other ECU functions where you obtain status and control. Memory access I just mentioned, so you can write and read from internal memory. The oscillator is fully integrated, no external component needed for that. And in case of a communication loss and in case of problems, the device enter a fail-safe mode, which is predefined. We have started the standardization and the CAN automation. So as said, the standard is an implementation based on a subset of CAN-FD. It is not a new network protocol, it's a subset of the ISO standard. We can still rely on the existing experience and tool set. We support existing hardware. And also we will define interoperability tests according to a subset of the ISO standard for interoperability. This CAN automation standardization has started, and there's a plan to go to the ISO afterwards. We do not include the physical layer, it's not needed. And the standard is needed for a major push towards the usage of the standard itself, because otherwise there will also always be the same chicken and egg problem. No one can implement this kind of network protocol because there is no standard. So therefore, nobody will deliver products with this network protocol, and therefore it will never be implemented. So the standard is absolutely needed if you want to implement a network into a car or in any other application. So here's the work plan from the CAN automation. So we have found a special interest group. This is the scope of the SIG that we developed this kind of network. And the schedule is we expect a work draft by summer 2021. In fact, yesterday we have agreed that we have a release candidate at least. So we have two more weeks for review. But then we think that we can go with this current standard with the 604-1 into a release state. So we are very optimistic on that, unless there is no veto within the next 2 weeks. And then we will move on with the conformance test and the system implementation. And I think we can get a release draft, at least of the standard, by end of summer or maybe in fall of this year, latest end of this year. And that's it. So thank you all very much.